This is Bluehound SSC, the most extraordinary and complex racing car ever designed. Built in the UK by a team of Formula One and aerospace experts, it aims to inspire a generation about science and technology and bring the world to a standstill by reaching 1,000 miles per hour, breaking the land speed record. Bluehound is a battle with physics, a journey into the unknown, a jet from a Typhoon fighter, a rocket hotter than a volcano, huge metal wheels spinning 170 times a second. With the equivalent of 135,000 horsepower, Bluehound will cover a mile in just 3.6 seconds, faster than a bullet. In 2017, the car will make its first test runs in Newquay, Cornwall, and then we'll be challenging for our first record on the Hackskeen-Pan in South Africa's Northern Cape. Here, a team of 300 people have moved over 16,000 tonnes of rocks by hand to create a smooth 12-mile racecourse on a dry lake bed. Driver Andy Green's first target will be a new record of 800 miles per hour. He'll return again later to push it to 1,000.
Wednesday morning, 15th of October, 9 o'clock in the morning. It's about 3 to 4 degrees outside. We're looking for a flat-out run through the measured mile, trying to get a supersonic two-way average today.
It's a popular misconception that driving a land speed record in a straight line is about anchoring the steering wheel, planting your foot to the floor, and just waiting till you run out of fuel. If only it were that simple. The car moves around an awful lot. Any road car moves around a little bit, and it moves around more so as you go faster. When you go a lot faster, like 700 miles an hour faster, the car moves around a huge amount. The wheels are now skimming across the surface, the shock waves are generating uneven forces, gusts of crosswind, the car is sliding all over the track. In terms of doing a run in thrust SSC, big intakes very close to the ground. I'd put very little power on to start with to accelerate the car without sucking lumps of desert into the intakes. So initially just inching the throttle forward, letting the car roll slowly, progressively, around about 80% RPM on the engine. That's quite a low power setting. Just letting the car accelerate no faster than a normal family saloon car would, pulling away from the lights.
SSC ready to roll.
SSC with fast chase rolling, you are clear supersonic.
Clear supersonic, SSC is rolling.
Rolling up through 10, 20, 30, all the way up through 50, 60 miles an hour. The reheat nozzles at the back of the engine start to close down to increase the thrust output. Now accelerating more quickly through 90, 100 miles an hour. Now got really strong airflow into the engines. Now I can spin them up very quickly. Ease the throttle forward to the dry stop. The turbines spin up to maximum speed. They are now working flat out. To get more thrust, neat fuel goes into the exhaust and literally reheats the exhaust. Reheat. Check that both needles are showing a light up so that both light together. If one lights and the other doesn't, the car's going to want to go in a circle, which is not good at supersonic speeds. Having got both lit, ease my foot all the way down, both nozzles open fully, we get absolute full power and the car is now accelerating at something like 25 miles an hour every second. 250, 275, 300, 325, and it just keeps going. at that speed, up to 500, up to 550, approaching 600 miles an hour. The airflow starts to go supersonic underneath the car, which affects the handling. It goes supersonic over the top of the car.
700, just about in control, on the wrong line, don't worry about it.
It's the loudest, highest pitched scream I've ever heard. The car tended to pull, because of the way it was constructed and the staggered rear wheels, tended to pull hard left at around 600 miles an hour. And that was requiring up to 90 degrees of steering lock to keep it straight. And on our first supersonic record run, it was such a hard pull, I actually had to throttle back to minimum reheat and close the reheat nozzles right down to reduce the thrust, rebalance the car. The car is now 50 feet offline, and I'm steering it effectively on the throttle at 650 miles an hour. As the car starts to respond, as soon as it starts to come back towards the line, I've got to put full power on or we won't get supersonic. And as it comes back to the line, take the opposite lock off, straighten the car back up. Now it's going supersonic. At over 700 miles an hour, all the airflow settles down, starts to go fully supersonic, and it runs absolutely as straight as a die.
700, just about in control, on the wrong line, don't worry about it. 730, it's a good here, biddy. Looking for express, flickering. Going to the end of a measured mile. Burners are still good. Excellent.
Through the timing lights, which took 4.5 seconds, about 4.7 seconds to cover the mile through the timing lights. Unbeknown to me, we're also throwing a huge sonic boom out across the desert. My job is still only half done. I now need to stop the car at the other end of the track. So throttling back at the end of the measured mile, we've now got warning captions for all of the oil thrown towards the front of the engines because it's slowing down so quickly. The low fuel caption is flickering. The car is now slowing down at over 1G, over 20 miles an hour per second, but very rapidly as the car gets subsonic. We've got a 10-ton car, very slippery 10-ton car, still hammering along at over 500 miles an hour. I'm waiting until the distance at the end, to the end of the track equals the speed I'm going, which is also changing. And when the two numbers match, punch out the parachute with a button on the left-hand steering wheel yoke, and immediately parachute goes out, generates another 4 or 5 tons of drag, and bumps the deceleration back up to 20 miles an hour per second.
450, shoot one. Yes, we got it. Everything is going to be wonderful.
The car is now going to slow down, and I'm still checking the numbers, slowing down through 400, 350, 300 miles an hour. There's about 2 miles left to run, 250 miles an hour, 200 miles an hour, we've got a mile left to run. I'm now going to shut the engines down. They've had a few seconds to cool. We don't want to ingest anything else. So shut the engines down, start to ease on the wheel brakes. I'm now looking about half a mile ahead, looking at the recovery crew, so that as we roll to a stop, I ease the brakes on and we stop exactly 14 miles from where we set off, right next to the guys who've got to turn a 10-ton jet car around, put the best part of a ton of fuel in, reload the parachutes, do a full systems and data check, and confirm it's safe to go back through the measured mile within 1 hour. So stopping in the right place is the key bit to starting the pit stop on the fastest car in the world.
SSC, the car is stopped, mile 13.5.
SSC copied. SS all stations standby. SSC has stopped, mile 13.5. SSC has stopped.
The drive then involves repeating all of that and subsequently stopping the car at the other end and waiting for the timekeeper to have recorded it. 15th of October 1997, he came back with those famous words, "Pit station, this is USAC timing, I have some times for you." And they were supersonic, and that record still stands today.
Today we carried out a load deflection test and a dynamic test. It's normally called a bump test. You hit the fin with a hammer or something, and you can measure the frequencies by an accelerometer. And depending where you hit it, you can excite different modes. You could get a frequency, running along the desert, you might get a series of bumps which can be at the same frequency and set off some vibration of the fin, or that coupled with some aerodynamic turbulence or something like that can start a flutter. So we need to look at that.
Right there, where this absolutely terrific.
Second part was a load deflection test to really validate the modelling that's been going on so far. So we loaded up the fin with up to just under a tonne of ballast in 6 stages, and measured the deflection at each stage. And at each stage we also had some strain gauge readings, which measures the stretchability of the spars. Where we were measuring from, which is probably 2/3 of the way up the fin, got up to just over 5 millimeters deflection. Some of that's due to the rig itself was twisting, which we also took into account. I did a model of this test, including the jig itself, and the deflection at the tip came out at just over 8 millimeters. So 2/3 down, 5 millimeters, it's of that order.
With the results closely matching the predicted data, the fin can be whisked off to Newquay, where it will run on the car for the first time the next day.
Hello, I'm Stuart Edmondson, Head of Engineering Operations on the Bluehound programme. I'm going to spend a couple of minutes just talking about where we are at the moment and what we're up to. As you can see, we're in front of our hardened aircraft shelter. These were built during the Cold War to protect Royal Air Force's aircraft, but now it's ideally suited for what we're doing at Newquay Airport. This is where we do all of our engineering, all of our pre-use checks, post-run checks, and I'm just going to give you a brief outline inside. Okay, as you can see, the central feature is Bluehound, the car itself, with suitable lighting all around. And you'll notice around the car we've got various bays that provide the necessary support from in the far corner, the mechanical side, and then on the right-hand side the systems team are based. If we come on in closer, we then also position some of the critical equipment out to the side, so you can see on the left-hand side here the canopy. And that's all ready to go. So when we've done our pre-run checks, obviously these items are the last things that get fitted to the car before we roll the car out of the HAZ. So here the final preparations of the cockpit, some slight adjustments. We're installing cameras so we can capture the action, and that's being done now, ready for our runs later today.
It's a competition to see how many engineers you can get in the cockpit at once.
Yes. As you can see here, one of our bays is a fabrication shop, and we've tried to replicate all of the facilities we had back in Avonmouth near Bristol. So we've got the ability to make adjustments, minor repairs and so on. So on this side of the hardened aircraft shelter, we've got all our systems team. They're based here with the ability to plug into the car, update data, make software changes, and also all of the cable looms can be made and manufactured here on the spot if we need to make any adjustments. And finally, we've got our ground support equipment, which is crucial, obviously, for preparation of the car, including the ability to refuel it, and also our air start unit, which is vital for starting the EJ200. We also have our cooling rig that is here to support us in cooling down the car post-runs. Okay, that gives you a brief summary of what the activities go on inside the hardened aircraft shelter, which is vital engineering checks prior and post all of our runs. But the second important aspect of our location is the fact we're only a few hundred meters away from the airfield where we conduct our dynamic testing. And in fact, we're due to do some of that this afternoon.
So this is the back of the EJ200 out of Eurofighter Typhoon. This is the nozzle system. When the car's running, this is not a place to stand. The combustion temperature inside this engine is 2,500 degrees centigrade. The decibel level out here is getting on for 200 decibels. On your airline you fly on holiday with, you don't have any of this. This is because this aircraft has to go through a huge amount of speed. So it goes from takeoff to supersonic to, in the case of Typhoon, around about twice the speed of sound. To do that with such a small engine, it uses reheat. So it puts extra fuel in the back of the engine, and that comes out as reheat or an afterburner. Because this has to do such a huge speed range, this nozzle needs to move to control the flow within the engine, and it's this part that makes it key to this being a supersonic engine. So it controls the flow within the engine to make sure it's not supersonic within the engine, and then it accelerates it to supersonic speed as it comes out. And you see that with those shock diamonds in that exhaust as it comes out as reheated flow. So here at Newquay, we're all about running the car down the runway, but actually engineering-wise, the most interesting thing for the project is the intake. So when we designed the car, this car goes to 1,000 miles an hour. So you have to have an intake that doesn't get too much air in there. So this actual shape here, we picked on Mach 1.1, so 800 miles an hour is when this intake works at its best speed, gets just the right amount of air in. And we said previously, the shape of the car going forward is all about controlling those shock waves. At Newquay, we're never going to get close to 800. We're hoping for around about 200 miles an hour. So when we started doing the slow speed testing here and the static testing was really to see how this would work at low speeds. And actually, with a slight headwind we had, it worked far better than we thought. That the shape, the smoothing it did, meant that the engine got just the right amount of air, and Andy could take it up to the sort of maximum dry setting. We actually got into a small amount of reheat when we were stationary. Now, the faster we go, the better this intake works and cleans the airflow up. So hopefully when we're running along the runway at Newquay, we'll be at full reheat, getting to 200 miles an hour.
A pencil-thin rocket car without any air intakes like the Blue Flame would seem to be the optimal design for a land speed record car. So why do both thrust cars and Bloodhound SSC have jet engines? Jet engines are a tried and tested technology. They're safe, efficient, and amazingly reliable, giving large amounts of power almost at the push of a button. Older engines are not too hard to find, but Bloodhound has been lucky enough to obtain a Rolls-Royce EJ200 as used in the Typhoon. Small, light, and hugely powerful, it's one of the most advanced engines available today.
We're clear this side now. So if we go down slowly.
Because Bloodhound is effectively a prototype, the development will involve making many runs of gradually increasing speeds, with the team comparing the data from the car with their earlier computer predictions. A jet engine is perfect for this, and with more than 20,000 pounds of thrust, the EJ200 can get the car to over 600 miles per hour. However, for the first test, the car is firmly tethered to the ground. The big questions are, will it work? And can we get reheat and a static test where no air is being forced into the small intake?
Bloodhound is designed to travel at 1,000 miles per hour. Now that's faster than the speed of sound, which makes things really interesting from an aerodynamics point of view, because we're going to be generating things called shock waves. Now at the nose of the car, we'll be generating the first shock wave the car will experience. It's called the bow shock. And it basically exists because the air hasn't had enough time to move out of the way of the car, to get around the car, so it has to suddenly compress. That compression causes a pressure increase and a temperature increase. So we anticipate that the nose of the car will get to about or just over 100 degrees centigrade at top speed. So as we move down the nose of the car, we get to the front wheels. And again, because they cause an obstruction to the flow, there will be more shockwaves forming ahead of these front wheels. Now, if you compare the shape of Bluehound with thrust SSC, which was much wider, that generated very strong shockwaves that caused real problems, particularly in terms of fluidizing the surface that the car was running across. Now, the design of Bluehound is far more slender and streamlined to try and minimize the strength of those shockwaves. So we're hoping that we're not going to see anything like those extreme effects that we saw on the thrust project. As we move further along the car, we arrive at the cockpit canopy that covers Andy Green, leading up to the jet intake. Now, this is really interesting because the intake to a jet engine wants the flow to be coming into it at about 500 or 600 miles an hour, much slower than the speed out here in the free stream, which might be at 1,000 miles an hour. So the job of this geometry on the car, even the cockpit canopy itself, is to generate a set of shockwaves that decelerates the flow of the air from 1,000 miles per hour out here down to about 500 or 600 miles an hour here. So that deceleration effect is happening over a space of just about 1.5 meters. So as we get to the rear of the car, we get to the rear wheels. Now, these wheels are rotating at 10,000 revolutions per minute, which makes the wheels actually simultaneously the fastest and slowest part of the car. Because at the top of the car, as that wheel rotates round, the top of the wheel is actually travelling forwards at 2,000 miles an hour. And then as the wheel rim rotates round to the bottom and touches the surface, instantaneously the bottom of the wheel is actually stationary. Now, in fact, we think that at the top speeds of the car, in fact, the wheel won't be rotating at exactly the same speed that the car is travelling at, because there'll be some slippage between the wheel itself and the ground. And that begs the question, well, how do we know how fast the car is travelling? So we can measure, there's another way of measuring the speed using a pitot tube. So on the fin, we've got a pitot tube mounted facing forwards. And basically what that is doing is measuring the pressure of the air that's being forced into that tube. And from the measurement of that pressure, you can then calculate how fast the car is moving through the air itself. But you still have a bit of a problem, because if you have wind gusts, that affects the reading on the pitot tube. So in fact, the speed that's measured on the pitot tube could be 20 miles per hour, 30 miles per hour, different to the actual speed of the car across the ground. So the most accurate way of us to actually measure the speed of the car across the ground is to use GPS. So the Rolex Speedo inside the cockpit of Bluehound is GPS controlled, but we'll be using a much more accurate GPS system than the kind of GPS system you would use on your mobile phone. And that's because we've got to get this really accurate, because the car will be covering a mile every 3.5 seconds at 1,000 miles per hour.
Hello, I'm Franz Niehammer. I'm the engineering manager here at Bluehound, and we're at the BTC. The car is about 3 weeks away from going off to be tested, so I'm going to give you a bit of a tour of what's been going on. So we've now got 2 EJ200s in the BTC. The one over there was being used for checking the fit on the car, but cannot actually run. This one here is fresh from Rolls-Royce, and it's all ready to power the car. So this is the upper chassis. Next week we'll be putting the EJ200 up into this structure. First off, we've got to complete cooling and sensor installation, which you can see around the upper chassis here. So here we are at the rear suspension. The discs and suspension have now been installed. You might notice these are carbon discs. We have carbon discs on the front and rear for Newquay. This allows us, with the tyres, to stop the car more severely than we could in the desert. So on the lower chassis, the team have been working hard to install the cooling systems we have on the car. So we have some air cooling ducts here. We also have some water cooling to keep the electronics cool throughout the car. So you may have seen the looms and the computer systems all laid out on the bench last time around. Well, here they are, all installed into the cockpit. There's not a lot of space to move around. It takes a lot of time and effort to get everything just right. It's amazing to think that with a car that's over 13 metres long, you'd be struggling for space, but here every little inch counts. It won't be long now before the engine's into the upper chassis, and the upper chassis is then onto the car, and we'll, in 3 weeks' time, be ready to take it to Newquay to run.
Hello, I'm Milton, and I'm a systems engineer on the Bluehound supersonic car. I do the power integration on the vehicle. So some of you might be wondering whether this is a cockpit mock-up and why we're not actually working on the monocoque, which is over the other side of the workshop itself. This is what we call a lab vehicle or a lab car. So all these panels and these switches and the instruments and the screens here you see are the real deal. But it's far easier to integrate everything on a bench and get everything working in terms of system integration. And then once we're happy it's all working, then we can transfer it to the car. If you kind of look at this as a mock-up of the vehicle, this is the blade, the front half of the vehicle, the cockpit, and way down the back there would be the rear half of the vehicle, the lower chassis as we call it. The power that's generated from the EJ200's generators is fed down to the front of the blade through a set of batteries to charge them, and then back into the cockpit. The cockpit really is kind of your main hub of the car, unsurprisingly, because that's where Andy does his work. All the analog signals on the car have to be converted to digital signals at some point and conditioned, and eventually fed up to the cockpit so Andy knows what he's looking at. But we have an awful lot of other signals that Andy won't be looking at on his screens, which we use for data gathering on the vehicle during the record attempt. So for instance, these are strain gauges, so we can measure the stress or the strain on various parts of the car structurally. There's a mass of wires, as you can see. These are in the process of being manufactured at the moment. All of this is signal wiring too, so there's probably close to 1,000 signals, I would imagine, on the car for sensors. So that's what we're doing this week, is testing this area, making sure we're happy with it, and when we are happy with it then we'll integrate the blade into the cockpit. When they're talking to each other then we'll integrate the rear half. So we try and work the team will try and work in parallel to bring things together all at once.
Until Bloodhound runs under its own power for the very first time, the only data we'll have for how it will behave will have come from complex computer simulations. The obvious ones are for aerodynamic loads, but the engineers have also made thousands of calculations to determine the enormous stresses and strains that the vehicle will have to endure. Pick a point anywhere within Bloodhound and you're never far from a sensor. There are well over 600 in total, and every time the car turns a wheel, they'll produce masses of information. With our new cloud partner, Oracle, we'll be checking the data in real time and using AI to predict where the readings are heading. So long as the data matches our predictions, we'll know it's safe to continue. Any unexpected results, and we'll stop until we've worked out what's happening. All over Bloodhound's surface, you'll find tiny holes, which lead to a plastic pipe and a pressure sensor. These are key to understanding the aerodynamics of the car. Although Bloodhound may be doing 1,000 miles per hour, there'll be some areas where the air is travelling much more slowly, and some where it's travelling much faster. Strain gauges use electrical resistance to measure how much an object is deforming, and consequently how big a load is going through them. They're attached to all the critical parts of the car where we expect to see the very highest forces, like on the suspension and fin. When you've got a rocket, a jet and a large supercharged engine in a confined space, it's going to get hot. So temperature sensors will make sure we're operating within a safe temperature range. There are also humidity sensors to make sure the many computers are dry, accelerometers to measure vibration and resonant frequencies, a pitot tube to measure airspeed, sensors that measure the wheel's rotation and movement of the suspension, sensors to measure fluid level so we can tell how much fuel is being used, lasers to measure the ride height, cameras to give us visual information, GPS to measure the ground speed and keep all the computers in sync, telemetry that records the driver's actions, and finally the driver himself. Thanks to Oracle, all this data will be shared live, so you'll be able to experience Bloodhound as if you were in the car too.
Welcome to Bloodhound, and a new series we're calling Anatomy of the Car. Over the coming weeks and months, I'm going to take you right from the front of the car to the back in full detail. Think of it as a video FAQ. In this first episode, we're going to deal with a question we've had a lot in the last few weeks. As we get going again, people have asked why, after the successful expo last year when we showed off a pretty much complete car, why are we taking Bloodhound apart again? Well, Bloodhound is a prototype, but it's also our final vehicle. And it's a cross between a fast fighter jet, a Formula 1 car, and a spaceship. And I like to think most closely it's like a spaceship. If Bloodhound had been a spaceship, how would it have been built? What would the stages have been? Let's talk more in the upper chassis. Let's use a space shuttle as a good example. There wasn't just one orbiter built and up it went into space. It was designed and built in stages with test and evaluation spacecraft that proved that all the bits, those 3.5 million bits in the space shuttle, went together correctly. For us, we don't have that many parts, but we could still fill a football stadium with all the people that designed and built this car. And at the end of last year, with all these big assemblies ready to check, we wanted to make sure everything fitted together the way we expected. And by checking those primary interfaces, we could be sure that we'd all done our homework right and we had a car that was going to work. So Bloodhound was designed and built in a very modular way, and there's lots of these primary interfaces we needed to check last year. The lower chassis to the rear suspension subassembly, the auxiliary jet tanks, the main jet tank, the APU, the trellis and the rails that go down the side, the main interface from the lower to the lower section of the monocoque, the HTP tank, the upper section of the monocoque to the upper chassis, and the intake. Lots of primary interfaces that we needed to make sure were working the way we expected. I'm going to go through all of these again in full detail over the course of this series. Here towards the front of the car, the goat's head, the front suspension subassembly, 4 large machinings that had to fit together and then accurately fit to the front of the monocoque. And here at the front of the monocoque, we have the key interface to the blade, which is the heart of the whole front of the car. Let's go and look at the blade as well. And this is the blade, the heart of the front of the car, and the last big interface I'll use as an example. The large panels that make up the front structure of the car all attach to this. So this needs to be straight, and this attaches to the front of the monocoque here at the end of the blade sections. So we did that drywall to make sure the car was true and straight and all of these big sections fitted together, as per these examples, but hundreds and hundreds of times over again. Once we knew the car fitted together the way we expected, we tear it all down, we check it all, and the next time all these parts come together, it'll be the final build of Bloodhound.
I'm Mark Chapman, I'm Engineering Director on Bloodhound SSC, and here to introduce the monocoque. So when we first designed the car, we were in now 2008, we made this decision to split the car into 2 different sections. So the front part of the car is carbon fibre, and the rear part of the car is metallic structure. The reason for that was the front part of the car is really curvy. There's a lot of shape on the front of the car, and we need that for many reasons, one of which is for Andy to be able to see the ground, but also to control the airflow into the air intake into the EJ200. Now, doing that in a metal structure is really difficult. It's really complicated, and there's a lot of work, a lot of fabrication to do to produce these shapes. So we went for a carbon fibre front structure, and this part here, the monocoque, is where Andy sits. It's his office, the cockpit. So with the monocoque itself, we've been really fortunate working with a huge number of partners on this, particularly SHD, who come up with the variety of fibres used on this. So we've got 5 different types of carbon fibre on this car. There's also aluminium honeycomb, and in some places it's over 25 millimetres an inch thick. It takes a huge amount of load and a huge amount of different systems that are bolted onto it. So we have, on the front here, we have the front suspension. We also have the blade that cantilevers off these mounting points here, and that takes all the front of the car that has the systems and the nose. The rear of this monocoque section, we have the HTP tank. So the HTP tank here contains over 1 tonne of peroxide, and actually just sits right behind where Andy Green is sat. So again, this huge safety cell is to make sure that the 2 most valuable parts of the car, so the rocket oxidizer and Andy Green, are kept as safe as possible.
When I was going through all the detail of the nose with some of the designers and engineers, Dr. Ben Evans reminded me that we've got a great episode of Cisco Bloodhound TV starring Ron Ayres, our chief aerodynamicist, that goes into the shape of Bloodhound in great detail. It's one of my favourite episodes. Check it out, the link will be below. When I sat down to talk to the guys and girls to understand why we came to the decision we did on the nose and its shape, it was really interesting, and let me share some of that with you. First of all, the nose is built in 2 sections, a titanium nose piece and then a carbon fibre main box. The titanium nose piece is made using an additive layer process. There's some other really interesting parts on the car that use the same process, so I'll come back to that in full detail when we get to those to explain just how that works. But in the first instance, the nose, it's made of titanium because it has to cope with quite a lot of erosion and high speed, and we went to look at that to see what the detail was. And chatting to Dr. Ben, I'd assumed wrongly that this would be the first part that would see supersonic airflow. And it's not. It's actually the rear wheel wells that are the first parts of the car to see airflow over supersonic speeds. So we'll get to that when we get to the back of the car. But the front of the car is still working incredibly hard. Whenever we see CFD drawings of the car, we'll note that the front of the car is almost always red, and that's because the pressure is really high. And it's seeing some incredible forces, and it's dictating the flow of air over the whole of the car from the front back. It generates some of the biggest shock waves, And again, I'd wrongly assumed that it would be the biggest shockwave on the car, being the first one to catch up with that air that hasn't had any warning that the car's coming, because it'll arrive silently when it's supersonic, but it's not. Again, the biggest shockwaves actually happen towards the rear of the car, but it's still a pretty impressive shockwave when you look at it. What does that shockwave do to that lead part, that titanium part? Well, it gets quite warm. Again, some scribblings from Dr. Ben, at 20 degrees desert temperature, we're likely to see 134 degrees of heating for that component. Now, that doesn't take into account a bit of conductive heat moving away into the rest of the structure, and a little bit of convective heat loss where the airflow going over the car when the car's moving a bit slower will cool it down. But this still is generating one of the biggest shock waves on the car. It's getting hot, it's getting eroded by any dust, and it's working really hard. Carbon fibre composites normally really light structures. In this case, this is quite a heavy part, but it makes sense when you start to think about how hard it's working on the car. I'll show you the inside so you can see the pressure ports. And you'll see these all over the car, and they're for collecting air pressure data for comparing back to the CFD. So the nose looks like a really simple part of the car, but it's actually working incredibly hard. Let's pop it in position and talk some more about what the load is. So I asked Dr. Ben, what kind of surface pressure is this part of the nose seeing? And he did a quick hand calculation for me, and it's 138,000 pascals. That's the same as not one, but two African bull elephants standing on the nose. Next time we're going to talk about the blade. The blade is at the heart of the front of the car, and it's made up of two large composite blade sections, some bulkheads in both directions, aluminium and carbon again. But in this case, at the front of the car, we had to be able to remove panels because we were now starting to package lots of systems and equipment inside the car. So with those panels removed, all of that equipment still had to be supported. So the blade had to be super strong, but also it had to connect to the front of the monocoque. Some of the systems that are installed are things like the hydraulic tank, and you can see how it's installed there. The nitrogen tanks, and you can see the number of tanks and how they're installed. And the battery systems. And all these systems, all this weight is hanging off the blade section, which is hanging off the front of the monocoque. So the blade has to be super strong. Let's look at the structure. So the blade section is made up of two very big, very strong carbon composite U-section beams. And there's a great episode of Cisco Bloodhound TV that talks all about how we make our composites, so check that out. The link will be below in the description. But this U-section is supremely strong. The two together, plus two big aluminium bulkheads, makes for a very strong, stiff structure. But it's still got to react all the way back to the monocoque on these spindly ends. But it's very, very strong in what it does. It's supporting all of that equipment. So it's an incredibly busy part of the car, and we're starting to see the packaging challenges where we're literally searching for millimetres of packaging space in a 13-metre long car. And all of this structure, the batteries, the nitrogen tanks, the hydraulics, the large panels, it's all hanging off the front of the monocoque and these connections on the end of the blade sections. Let's go and take a look. And all of that front structure mounting off the blade is then connected to the front of the car on the monocoque here, here and here. And that wraps around the front suspension subassembly, also known as a goat's head, and we'll talk about that in the next episode.
So with our partners Nammo, we're about to witness the test firing of their hybrid rocket motor in their test facility in Norway. For us at Bloodhound, it's immensely exciting because this is the motor that's going to take us to break the record, developed with ESA, the European Space Agency, a hybrid rocket motor that's going to power the future generation of spacecraft. And that's what's going to be powering the car from next year. So for us, it's a really important test.
This is the Nammo hybrid rocket. It's a hybrid rocket because it's using a liquid oxidizer, in this case hydrogen peroxide, and a solid fuel. The oxidizer passes through this pipe here. It's then going to pass into the catalyst pack here. The catalyst pack degrades it into both steam and oxygen at very high temperatures and pressure. The pressure coming through here is apparently enough to fill a bath in 3 seconds or so. It's then going to pass into the combustion chamber where it mixes with our fuel. As it then combusts, this will get extremely hot and then pass out through the nozzle off this way.
Hybrid rockets are relatively new technology compared to other types of rocketry, and it's the safety element that really appeals to us. This is going to provide half of the thrust that leads us to 1,000 miles an hour effectively, so it firing is a very big milestone for us.
10, 9,
8, 7, 6, 5, 4, 3, 2, 1. That's perfect.
From our perspective, it was really good because there were no real surprises. So the rocket burned very efficiently. You can see that from the really clean rocket efflux. It's a huge step forward and massive confidence boost for us running in the car next year.
Jet intake duct test. The reason why we're doing this is we want to check that should the jet engine surge, that the inlet duct on the car will not burst. So this is the front of the inlet duct. On here you can see a couple of sensors for today's test. We've got a pressure sensor here, which measures the pressure inside the bag, which is pumping up the inlet duct. As well as that, we've got strain gauges, which measure the strain on this inlet duct as we pump it up, so that our stress engineers can check that the modelled strain that we see on the inlet duct matches reality, and that's the point of today's test.
Bag's gone. What's happened is it's obviously had a lot of tension on this edge, and because it's got a sharp edge, it's got a huge stress razor on the corner that's ripped it, and then the moment it's let go, you've suddenly lost that load, that link, and that's why it's kinked.
Don't break it.
About 21.
That's a minute, isn't it?
It's 2 minutes.
It feels like 3 or 4.
The inlet duct, so far as we can tell, has deflected quite close to the modelled deflection in the stress, but that needs to be analysed a little bit further. That's above the intake pressure that we'll be seeing at 1,000 miles an hour, so that also, I suppose, kind of cater for the just general usage of this inlet duct at 1,000 miles an hour.
So with a land speed record car, it's very key to get the wheel just right. So the cars you see running here on Kalahari Speed Week and the Bonneville Speed Trials, they run rubber tyres. And the reason they do that is they've got driven wheels, so their engines are driving the wheels, they need traction. Rubber's excellent for that. Around about 400 miles an hour, as the wheels go around faster and faster, the tyre peels off the rims and it comes off. So you then have to go to a solid wheel. So we've chosen aluminium, and basically these trials are to verify not only the material we've got, but it's that final bit of the profile, so whether it digs into the desert or whether it's very smooth. And it's very key, this surface is unique, and it is Andy Green's looked at an awful lot of places, and this is the one place on the world that will become the world's best place for breaking land speed records.
And action!
Right, the main objective is we're trying 2 new wheel profile shapes on the pan here. We came out in November last year to do our first testing out here, and it became very clear that the wheels we were using were cutting through the thin mud layer on the top of the surface and running on the hard kind of bedrock that's below the kind of mud you get on the top. And we were seeing quite a lot of damage to the wheel as it was running on the surface. So we've got 2 new wheel profiles here today that are flatter. So the idea is to try and get them to run on the mud surface and not run so deeply sort of embedded in the ground. If they run too shallow though, then we'll lose any kind of lateral grip because they have to dig in a little bit to get some kind of grip. To start with, we're going to just run the trailer down the desert for a couple of kilometres and then add some more water ballast to the tanks, and then we'll work our way up to the full car weight. And then we can monitor how far the wheels go into the dirt as we increase the weight. And then what we'll also do is we'll drive the lorry in some circles, and if we know the speed of the lorry and the radius that we're going around, we can work out how much lateral grip we've got. And by looking at the indents into the mud, you can see how much the trailer wheels are actually sliding. And from that, we'll get a pretty good understanding of the lateral grip as well. So that's the plan anyway.
It's been really good. I mean, today we ran the trailer with the heaviest weight, so it's now pretty much what the car will weigh on one axle. The straight line tests, basically the flatter wheel is running to its full width, so it's getting some lateral grip, but there's a concern that it's kind of digging in at the edges. The V-shaped wheel hasn't broken through the surface at all. It's been showing really good stuff. It's not been damaged at all by any rocks that are in the surface. And we've just done the circle tests either way. And fair play, it's been pretty impressive. The trailer has just started to move in both directions, and yeah, it's showing that we're getting fantastic grips. I think it's been really successful.
Yeah, I mean it's excellent. I mean it's really interesting looking at how the 2 wheels behave differently. We obviously made them very different, so we could definitely see a difference. And now we've got the previous data we collected in November and the data from these 2 wheels. So from this we'll be able to design the optimum profile, should I say, for the wheels for the first year. And then when we start running the car, obviously we'll learn an awful lot more about how the wheels are behaving with the real car. But this is the first major sort of hurdle you've got to get over into designing the actual profile. Our brakes are unusual because they've got to survive at 10,000 RPM, but we only use them from 160 miles an hour downwards. So initially we tried using these carbon rotors that were off a fighter aircraft, but unfortunately they wouldn't survive above about 5,000 RPM. And as you can see, we have some of the results of the failed discs here. This is a runway disc for the Bloodhound car, but the desert discs are a similar size, and as you can see, they're quite large and they're quite difficult to package in the front of the car. We try and keep everything as narrow as we can, and as a result, the front upright on the car has ended up having the caliper actually built into the upright. Because the wheels have very little grip on the desert surface, we can't use the brakes to their full potential, and as a consequence it takes us a lot longer to stop than you would with a normal car, and it's a bit like trying to stop on a very wet road.
It was decided that steel would be the most suitable material for the discs, but they would need testing to make sure they didn't warp or become brittle at extreme temperatures. AP Racing's test rig uses a huge flywheel to simulate the weight of the car, and at over 6 tons, Bloodhound would push it to its limits. 4.6 kilowatts of energy was scrubbed off in just 19 seconds. Although the disc surface reached temperatures of over 850 degrees centigrade, it performed perfectly and could be used several more times. The next test will be to see if they can survive the 10,000 RPM spin test that destroyed the carbon discs.
This is the cockpit of the Bluehound supersonic car, my 1,000 mile per hour office. It's a carbon fibre monocoque. It is a single piece with all the structural strength built into it. And carbon fibre is an extraordinary material. It is the same high technology material from which we make modern jet fighters, Formula One cars, and in this particular case, the strongest safety cell in the history of motorsport. It is 7 layers of carbon fibre with then an aluminium honeycomb spacing and another 5 layers on the inside. This has produced a monocoque which is a total of 200 kilograms and took over 10,000 hours work to produce. It is a fantastic piece of technology and it needs to be phenomenally strong. To take the loads and the thrust from 210 kilonewtons, 130,000 horsepower of engine thrust at the back of the car, and to take the aerodynamic loads of up to 12 tons per square metre, and the suspension loads from the front suspension bolted on here. Boeing AMRC made this for us, and itself is an extraordinary piece of technology. 4 pieces of aluminium, each over 200 kilograms, were forged multiple times, literally heated and squashed to actually shape the grain to increase the strength of the aluminium. It's exactly the same process we used to manufacture the wheels, which you can see in the BHTV clip. Then they were machined down, so 800 kilograms of aluminium has now become just over 40 kilograms of aluminium. The rest goes for recycling, and we now finish up with the structural heart of the suspension. Onto the sides here, we're going to have double wishbones bolting, plus the dampers and the spring suspension. On the end of that, 2 90 centimetre diameter, 100 kilogram wheels will be spinning at over 10,000 RPM. The total suspension loads designed to take over 30 tons at the front end. So these are the sorts of forces that would tear apart any normal race car, any normal road car. This is an extraordinary piece of extreme technology. All of that load has to be passed through this aluminium into the carbon fibre monocoque, which is the structural heart of the car. The canopy has to do several things. First of all, the windscreen has to keep the wind off my face. At 1,000 miles an hour, it gets very windy. There's a hole here physically to allow me in, but most importantly, it is a key aerodynamic part of the car. Because out here, the airflow is doing over 1,000 miles an hour in this direction. Back here, we've got a jet engine which needs to have the airflow going less than 750 miles an hour, below the speed of sound. Otherwise, it breaks down as it hits the blades. So we actually have to slow the airflow down through about 300 miles an hour or more in this distance. So the shock waves coming off the canopy, off the top of the canopy and across the start of the intake are a key part of the airflow system for the jet engine. To give you an idea of the volume, if you opened your front door and saw this picture, with the jet engine running at full speed, it would suck all of the air out of your house in about 3 seconds. The whole house, it would empty. 200 cubic meters would go down there in 3 seconds. The flow rate is just phenomenal. So the airflow management here and the speed management is an incredible challenge. Of course, the other key part is being able to see where I'm going. This is where the canopy will go. We've got the mock-up here because the real one is away, having the acrylic windscreen fitted to it right now. They literally take a block of hot acrylic, and the PPA group are actually stretching this and wrapping it around a mould, which will produce about a 12mm piece of plastic. And they'll do that twice. They'll then glue these 2 pieces together to make them even stronger. So I've now got a 25mm thick piece of plastic. And I'm looking through it at a very shallow angle through here. So I'm actually looking through about 50+ millimeters of plastic, curved plastic, which needs to be optically perfect so I can see what I'm doing. That curved plastic is that thick and that strong to survive the 1,000 mile an hour airflow, and also, worst case, to take a bird strike from a big bird, maybe 2 kilograms at 650 miles an hour. or half that weight at approaching 1,000 miles an hour. All of this technology will give me the most extraordinary working environment with which to get Bloodhound up to 1,000 miles an hour, and also the highest level of protection we can possibly get. It's a brilliant piece of engineering. This is the Bloodhound SSC cockpit, my 1,000 mile per hour office. This has literally been moulded around me, and it's just big enough to take the screens, the controls, and the seat that will both protect me and allow me to control the world's fastest car. The steering wheel has been printed from powdered titanium, so there is a zero waste printed steering wheel which has been made to exactly the profile of my hands. On that I have the control buttons for the parachutes, air brakes, and also for the rocket with the 2 trigger switches. That'll control the car underneath my feet, the right hand pedal for the throttle for the jet engine, left hand for the wheel brakes. The centre screen gives me performance and particularly a lot of information on the speedometer. Not only the inset power from the jet engine and the rocket, but critically when I need to put the rockets in and what peak speed we're going to, and then slowing down when I put out the air brakes or when I put out the parachutes, depending on what we're using, and when I put in the wheel brakes. Because the speeds for each of those is absolutely critical. Too fast for the parachutes, they will tear off. Too slow for the parachutes, we're going off the end of the desert. And going cross-country at 300 or 400 miles an hour in this car is not a good idea. And the worst case, if that instrument stops working, if the screen physically goes dead for some reason, then the Rolex speedometer below it and to the left gives me an exact copy, fully reliable with its own GPS and its own power system, so that whatever happens, I can stop this car safely from any speed, regardless of any other failures. Right alongside the speedometer, the other critical thing for this car is the wheel loads. We have spent over 5 years developing the aerodynamic model to keep the car on the ground at all speeds, so that we don't generate any lift, and equally important, we don't generate any download. Every single test run we do will be increasing the speed, and I will be checking at every stage the downloads on the wheels. If they're getting too low, we will abort. If they're getting too high and overloading suspension, we will abort. So while I'm watching the speed critically, I'm watching those wheel downloads right next to it all the time. Everything else is very much status and will only become of interest if we start to see these orange and red colours flashing up with problems. Right hand is all the power systems, engine cooling, etc. All of the switches to control the jet engine, the rocket motor, and the race car engine that powers the rocket motor. The left hand side is the electrics, hydraulics, etc. with the switches to control them below that. And on the other side, the Rolex chronograph, which gives me precise timings for jet engine startup, cool down, anything else I need during the profile. Everything in the cockpit is controlled with electric buttons and switches, so everything is right there at my fingertips. But if something goes wrong, if we have a power failure or an electronic problem of some sort, then I have backups for the safety critical systems. Specifically, on the right hand side here, I've got a lever that will physically, mechanically shut off the fuel supply to the jet engine. And on the left hand side, I've got 2 levers which will actually pull cables that go all the way to the back of the car, and they will physically pull a pin from the parachute mechanism and deploy the parachutes, so we can get to 1,000 miles an hour and stop the car safely, whatever happens. Sitting here in the cockpit, there's going to be a lot going on. There's a 400 mile an hour deceleration going on over here, so huge shock waves, an incredible amount of noise and energy directly above my head. It's also going to be hot because it's a sealed cockpit, we're in the desert, and there's the G-forces, accelerating at 2G, decelerating at 3G. That's losing 60 miles an hour per second. So it is going to be very noisy, very hot, very uncomfortable, and physically demanding. And at the same time, I'm monitoring all of the instruments in here, using the controls to control the car very precisely, very accurately, to make sure we get up to exactly the test speed on each day, and ultimately to 1,000 miles an hour, and then stopping again safely.
All rocket types need 2 basic ingredients, fuel and oxidizer, so that the fuel can burn. Solid fuel rockets are the most common. Here a powdered mixture of solid fuel and oxidizer is packed into a casing. Once it's ignited, the mixture rapidly combusts, propelling the rocket forward. It's very simple and safe until it's lit, but has one drawback: it's not easy to turn off. In a liquid rocket, liquid oxidizer and fuel are kept in separate tanks. These are then pumped into a combustion chamber where they react violently with each other, sending hot gases out of the specially shaped nozzle. The rate at which the liquids are pumped can be varied to alter the amount of thrust, and it can even be shut off altogether. But if these liquids accidentally made contact outside of the combustion chamber, they could cause an explosion. The third type of rocket uses elements of both other systems. The oxidizer is stored separately, and the fuel forms a solid lining on the inside of the rocket tube. In Bluehound, the oxidizer is high-test peroxide, or HTP. It is pumped through a silver-plated catalyst, which causes it to decompose, releasing very hot steam and oxygen. This is hot enough to ignite the fuel itself and create thrust. It's a fairly safe system, as stopping the flow of oxidizer will stop the rocket, and the fuel is a harmless rubber mixture. Our resident rocket expert has built a small hybrid rocket which we can run in the workshop. It uses a perspex tube as the fuel, so that we can see what goes on inside.
As you can see, this is just a stick of plastic, and I guess the worst thing that could happen is you could drop it on your toe. So we'll ignite the hybrid on a count of 5, 4, 3, 2, 1, go.
Stop it on a count of 5, 4,
3, 2, 1. Although the motor we'll be using on Bluehound will be quite different in terms of size and oxidizer, in fact it'll be hydrogen peroxide instead of oxygen that we've used today. It will also use a slightly different fuel that's based on rubber instead of acrylic, and obviously it'll generate a great deal more thrust, but the principles are exactly the same. And in fact the safety of it should also be almost identical, which again is very, very important for our vehicle where we have Andy Green driving it, and he'll want to be able to shut off that rocket motor at any point that he deems necessary.